the acid dissociations which are occurring in this reaction. So first we have H3PO4, and that dissociates into H2PO4. Okay, and what else? H plus. Yeah, so H plus and H2PO4 minus. So this is the conjugate base of H3PO4, but this also behaves like an acid, so we have H2PO4. That dissociates into and the charge of HPO4, yeah, it's 2 minus. So again, this behaves like a base. It also behaves like an acid. So in our last one, we have HPO4, 2 minus going to H plus, and PO4, 3 minus. Let's look up the Ka of each acid. Then we can calculate pKa too. So to find the Ka, we can take a look in table 16.4, and for phosphoric acid, the Ka is 7.5 times 10 to the minus 3. For the dihydrogen phosphate, it's 6.2 times 10 to the minus 8. And for the hydrogen phosphate, it's 4.8 times 10 to the minus 13. So what I'd like you to do is to calculate the pKa for each acid. Then we can start filling in the information on this table or this graph. Okay, so the pKa, and we'll call this one pKa1, which corresponds to this Ka is equal to
1.12? 1.12.
1.12? Are you sure?
I'll double check.
I think it's 2 point something. 2.12, okay. And what about for this one? 6.8 times 10 minus 8 corresponds to a pKa of 7.21. 7.21. And then for the last one, 4.8 times 10 minus 13, you can take the log of that, and that's equal to 12.2. Okay, so we know using the Henderson-Hasselbalch equation that at the halfway point, A minus equals HA, so the pH equals pKa. So can we fill in the pHs at the halfway points right now? So at the first halfway point, the pH is equal to 2.12. So this is at 2 point. Okay, this is at 2.12. At the second halfway point, the pH is equal to, let's see, what is that? 7.21. And at the third halfway point is equal to 12.3. Now, we can use this equation here. At the first endpoint, the pH is equal to pKa1 plus pKa2 in 1/2 of that. So let's add up pKa1 and pKa2 and then divide that by 2. So in that case here, let's see, this is 2 point, okay, so first at the first end point, pH is equal to 1/2 pKa1, which is 2.12, plus pKa2, which is 7.21. So we do the math there.
8.27.
Okay, so at the first endpoint, the pH is equal to 8.27. We can do the same thing at the second endpoint. So at the second endpoint, pH is equal to 1/2 pKa2 plus pKa3. Okay, so that's going to be 7.21 plus 12.3. So that's going to be 19.5 divided by 2, and that's equal to
13.36.
what was that again?
13.36.
13.36. Are you sure? Because see, it's got to be between 7.21 and 12.3.
5.7.
What is it again?
5.7.
5.73, are you sure? No, it's got to be between 7.21 and 12.3.
It's like 9.
9.7. What is it again? 9.76? Okay, so we did the easy ones. Now we got to figure out the pH at the starting point and then the pH at the third end point. So what equation do we use to calculate the pH at the starting point?
The negative log of the molarity?
No.
Is this a strong acid?
No, it's based on the Ka, note that H3PO4 is a weak acid. Yeah, so we just can't assume that the 0.1 molar is going to be the molarity of the concentration of H+. Okay, so for weak acid at the starting point, only HA is present, so we want to use Ka. So which Ka value do we use to calculate the pH at the starting point? Ka1, Ka2, or Ka3? Okay, Ka1. So what we can do, so at the starting point, we'll use this equation here. So we have H3PO4. Okay, so you know what to do is you have the initial amount, the amount that reacts, the amount of equilibrium. So the initial concentration of H3PO4 is equal to 0.1. And then for H+, the initial amount we said was 0, and that's also 0. So I'll let you guys fill in the rest of the blank so you can calculate the pH at the starting point.
Mr. Yee?
Say it again.
The first endpoint.
Yeah, that's it's 4.67.
Here,
Yeah, that one.
4.67. Yeah, so it doesn't make sense to go from 2 to 8 dynamics. Good, thanks.
There you go.
Thanks for catching that.
I was about to tell you that.
Omar.
Would you ever get a graph like that where you gotta get like a peak and then you come back down?
Well, let me say this. You could do an experiment, but then you probably need to do something wrong. Or something's wrong with your instrument if that happens. No. Yeah, we can't assume that all of it reacts because it's a weak acid, based on the Ka value. Yeah, so what you want to do for the amount that reacts, use your favorite variable. We've been using x. Should we use a different variable this time? Z or A? X? Yeah, so use your favorite variable, whatever that is.
Can we use O?
If you want to.
Because that get kind of tricky because you have already have to.
Yeah, then you have to distinguish between the 0 and the O. Okay, so then at equilibrium you have 0.1 minus x and then x and x. And then from there, what's the next step? I'll do it on this side of the board. So at the starting point, we have, let's see, what is it? X times x divided by 0.1 minus x. And that's equal to Ka1, and that's equal to 7.5 times 10 minus 3. And can we use our simplifying assumption by saying that x equals 0 here? Yes, let's do that. So if you solve for x, 0.024. Now note that x is equal to H plus. So from here we can calculate the pH, so the pH is equal to minus log of 0.024. 1.56. So that's going to be the pH at the starting point, 1.56. Okay, so we've got one more to go. pH at the third endpoint. So how do we calculate the pH at the third endpoint?
Will just be all the base, right?
Yeah, so only the base should be present. So when we do it for the monoprotic gas, we say at the endpoint only A minus is present as base, like Joyce. Now, which base is going to be present? So note that depending on where we are, it's either going to be the H2PO4 minus, HPO4 2 minus, or PO4 3 minus. So at the third endpoint, which base is present? Okay, so here's what's happening. So initially, at the starting point, H3PO4 is present. As hydroxide ion is added to the base, we get the H3PO4 reacts, H2PO4 minus is produced. At the halfway point, what substances are present and in what amount? Yeah, so at this point here, we're going to have,
H plus.
yeah, we know that, but the phosphorus compounds. Okay, so remember at the halfway point, A minus equals HA. So at this first halfway point, you'll have H3PO4. And then that concentration will be equal to H2PO4 minus. So as the titration continues to occur, now after the first halfway point, you'll have more H2PO4 minus and less H3PO4. At the first endpoint, what phosphorus compound will be present? Okay, so it says here only A minus is present, so the A minus at this point is going to be H2PO4. So at this we have H2PO4 minus. We continue to add hydroxide ion, so at the second endpoint what substance is going to be present?
H2PO4 and H2PO4.
Yeah, so we're going to have H2PO4 minus, and that concentration is going to equal HPO4 2 minus. So as the titration proceeds, now we're going to have more H2PO4 minus, less of H2PO4 minus, and at the second endpoint, the substance which is present is HPO4 2 minus. Then as more base is added at the third endpoint, we'll have, yes, you'll have HPO4 2 minus, and that's going to equal the PO4 3 minus. And finally, at the third endpoint, we're going to have PO4 3 minus present only. Now note the other thing which is happening. As the pH changes, the charge changes too. So for example, at a pH of 4.67, the charge of your solution is -1. At a pH of